Hi everyone. I just wanted to consolidate this section with you of inflation, monetary rates, and real rates so that we can just consolidate the ideas that we've learned so far and make sure that you have a solid understanding of them. Okay, let's go. So, as with all things in FinMath, this whole story starts off with a timeline from time 0 to sometime in the future t. And at time 0 we have an amount, we'll say a0, and at time t we have a future amount, we'll say at. Now at is the accumulated amount at time t. At is the accumulated amount at time t specifically, and this means that at is a monetary value, because if you recall, a monetary value is a future amount at a specified future time. And an example of this would be 200 at time 2, or 100 at time, let's say, 10.5, or something like that. Just so long as it's a specified future amount at a specified future time, then it's a monetary value. In this case, at t equals t is a monetary value. So just to confirm, at is the accumulated amount at time t. So we have a specified time here, t, which makes at a monetary value, because a monetary value is a future amount. But not only is it a future amount, it's a future amount at a specified future time. So it's given in terms of a specified future time, for example, 200 at time 2, 100 at time 10.5, etc. This makes it a monetary value. Okay? Okay. Now, A0 is the amount at time 0. A0 is thus a real value. Now, why are we saying it's a real value? Because a real value is an amount at any time t is greater than or equal to 0. It's an amount at any time t which is greater than or equal to 0 in terms of time 0 money. So this adjusts for growth due to inflation or loss of purchasing power. So a real value is any amount really which can be at the present or in the future. By the way, a present value of an amount, so if you're at time t and you're given an amount at time t, that value will always be a real cash flow. Cool. So a real value is an amount at any time, any positive time t, in terms of time 0 money, time 0 being the present. So any amount at any time t that is expressed in terms of the present, in terms of the present purchasing power of that money, then that value given is a real value. And it's a real value. It adjusts for growth due to inflation, or you can say that it adjusts for the loss of purchasing power. That's another way to put it. And so the real value equivalent of time t, we said at is a monetary cash flow. The real value equivalent of at would be at times 1 plus f to the minus t, where f is the annual inflation rate. In other words, if we take this future amount in terms of the purchasing power of the money at time t, and we adjust it for inflation, in other words, we reverse the growth due to inflation that happened during this period, we reverse this growth that happened and bring it back to time zero, then we'll have a real value. And this brings us on to an important relationship between real rates and monetary rates. So say R is a real rate, I is a monetary rate, and F is the inflation rate. All effective and constant. So we're not dealing with nominal interest rates here. We're dealing with effective rates that are constant throughout the time period. This is just for mathematical ease for us. So look at what we did here. When we describe the future amount AT in terms of the purchasing power at time zero, AT, we first reverse the inflation growth that happened in this period, in which case we describe AT in terms of time zero purchasing power. And this gave us the real value of AT, but it's still at time t. And so now that we have the real value, we present value it using the real rate. I hope that makes sense. So we present value real values or real cash flows using the real rates. This is a real cash flow. This is a real cash flow, and we present value real cash flows using the real rate. We present value real cash flows using the real rate. And this is equal to just AT 1 plus I to the power of minus t. This is a monetary cash flow, which we present valued using the monetary rate. So it's important and worth noting that we present value real cash flows at the real rate and monetary cash flows at the monetary rate. Why is this distinction important? Because in FinMath, you'll often find questions which ask you to find, given certain cash flows which are real or monetary. Usually they'll give you monetary cash flows, even nominal cash flows, and they'll ask you to determine the real rate R. And the tricky part about this is you can't determine R by present valuing the monetary cash flows directly. You have to first change, in often cases, to find R. The method is, so given monetary cash flows, this is an oversimplification, by the way. There will be little nuances here and there that you'll have to account for, but generally this is the method. Given monetary cash flows, I'm going to say CFs here, we first convert monetary cash flows into real cash flows, and then make an equation of value using the real cash flows, and then solve for the real rate R. That's usually the method. The reason why we need to distinguish between the real cash flows and the real rate, and the monetary cash flows and the monetary rate, is that you cannot present value real cash flows with monetary cash flows. You cannot present value monetary cash flows with the real rate. You have to use the corresponding rate for the corresponding cash flows. Real cash flows are present valued or accumulated using the real rate, and monetary cash flows are accumulated or discounted using the monetary rate. Now, the relationship that's very important that we saw not quite clearly using this illustration is that 1 plus, if we accumulate something at the monetary rate. Okay, let me draw a timeline just so everyone understands. We'll go from time 0 to time 1, and we start with some investment 1. Okay, we start with some investment 1. Now, I hope you'll all agree with me that moving from time 0 to time 1, there is two types of growth that's happening during this period. Two types of growth. Okay, so firstly, it's the growth due to interest. So we know this, when you put a certain amount in a bank that earns interest, compound interest, the interest compounds and causes the amount to grow. So there's growth due to interest, but also realistically in the economy, we have to account for the fact that there's growth due to inflation. Okay, so getting to this amount here, 1 plus I, is the accumulated amount here, okay, of 1 rand at time 1, if we assume the interest rate is I. This accumulated amount at time 1 is growth due to the real rate of interest. So I shouldn't have said I should have said growth due to interest, which is the real rate of interest. So this is the real growth that separates out inflation. There's growth due to the real rate of interest, which is separated from inflation or adjust for inflation. And there's also growth due to inflation itself. So this monetary accumulation factor is the product of the accumulation factor due to the real interest and the accumulation factor due to inflation. In other words, this monetary accumulation factor accounts for both interest and inflation. Okay, so this is why we accumulate real monetary cash flows using this value, because monetary cash flows have inflation in them. We said a monetary cash flows is a specified future amount in terms of the purchasing power at that future date. So it has inflation in it. The inflation has not been adjusted out of it. So we're accumulated and discounted using the monetary rate to ensure that when we discount, we also discount inflation. And the real rate, which we use for real values, it takes out inflation. From this relationship, we can see that if you want to accumulate using the real rate, you accumulate using the monetary rate and you divide it by the accumulation factor for inflation. In other words, this is adjusting for inflation. Okay, this is adjusting for inflation. Okay, cool. So I hope you understand what we've done so far. Now we're going to look at like different methods of kind of measuring inflation growth. Or before we get to that, we need to discuss something called a nominal value. So we have a monetary cash flow or a monetary value, which is a specified future amount at that specific future time, or in terms of the purchasing power at that specified future time. And we have a real value, which is a certain amount at a certain time t is greater than 0, expressed as in terms of the present purchasing power. Now, a nominal value is a percentage of the face value of a security. So in other words, this does not tell you the amount in terms of a future time, nor does it tell you the amount in terms of the present time. For an example of a nominal amount is if I say a bond um, a bond of 100 Rand nominal, redeemable at 105%. Let's say this is for more specificity, a 1 year zero coupon bond. Okay, a 1 year zero coupon bond of 100 Rand nominal, redeemable at 105%. Now, the redemption value, the nominal redemption value, will be equal to 105% times 100, which is equal to 105. Okay, this is a nominal value. The reason why it's a nominal value is because, first of all, it's a percentage of the face value, which is 100 Rand nominal. It's 105% of the face value. In other words, they're not telling you that, hey, in 1 year you'll get 105 Rand, or in 1 year you'll get 105 Rand in terms of today's purchasing power. They are merely telling you that, hey, we don't know how inflation is going to work. We don't know how this value, how the purchasing power will go up and down. All we know, or all we can tell you, is that in that specified future time, we'll be able to give you a certain percentage of the nominal value, however much that nominal amount is worth at that particular time. So for this nominal value, this nominal value is neither monetary. Because of this, it's neither monetary nor real. So first, if you have a nominal value, you have to convert it to a monetary value. How do you do this? By inflating it. First, you have to inflate it and then convert it to a real value by then deflating it. And I know these effects look like they cancel out, inflating and deflating, and the truth is they won't in the cases that you're going to get to work with them, which are the cases where you use indices, inflation indices, to denote inflation, where the indices are lagged, in which case inflating it and deflating it won't cancel each other out necessarily, because you'll see later onwards the lag makes the difference. It's not like you're saying 1 plus f to the minus 1, which is equal to 1. You're not doing that. It's something different. The case in which we use this is different, so they won't cancel each other out. But just to confirm this, a nominal value is a percentage of a face value that you'll be given, in terms of. So let me say that again. A nominal value is a percentage of a face value that is neither monetary nor real, because it does not tell you the amount in terms of the future purchasing power or the future time, and it's not real because it does not tell you it does not tell you the amount in terms of the present time. So all it tells you is that you'll get a specific percentage of the nominal amount at that time, and you'll have to work out what that percentage is worth at that time by inflating it and turning it into a monetary cash flow, and you have to work out how much that particular percentage is worth in terms of time zero money by deflating it. Yeah, so I hope that makes sense. But we're going to do an example just to make this easier, just to tie this all together. So if you don't understand, just hold on to your confusion a bit longer and try to follow along. And the last thing, or kind of the last conceptual thing that we're going to learn, just to kind of close this off, is the issue of inflation indices and lags. So inflation indices and lag. So another way in which we denote inflation, in terms of instead of just denoting it as a constant rate, we can denote it in terms of an index. It can be a retail price index or the consumer price index. So let's make this a bit smaller. So instead, we're gonna have a timeline here: time 0, time 1, time 2, time 3, time 4, time 5. Okay, now the first part of this, we're gonna do the non-lagged version of this. So to denote the inflation growth during the period, they'll tell you that the retail price index or the consumer price index or whatever index that you're given, they'll give you specific values at each of the specific time points. So they'll tell you that the index has a value of 97 at time 0, 99 at time 1, 105 at time 2, 108 at time 3, 109 here, and 111 here. What do these values tell you? Well, these values tell you the growth. This is when inflation is non-constant. Inflation growth is non-constant during the periods. Okay, so the growth during this period will be 99 minus 97 over 97. That would have been, this is the inflation rate, the equivalent inflation rate during this period. Likewise, the growth during this period would be 105 minus 99 over 99, which is the inflation equivalent for this period. So we use indices when the inflation rate is not constant throughout the periods. And how would you denote, so knowing this in mind, how would you denote the growth of a particular value? Let's say you're given a cash flow of you're given a cash flow of 1 year. We want you to denote how 1 will grow due to inflation only from time 0 to time 1. Well, you'd multiply 1 by 99 over 97. That's how you denote if inflation growth. Okay. Likewise, if you're given an amount here, is this correct? Okay, sorry about that. So if you're given a real value A0 and you said this is the real value at time 1, in other words, this is the value of a particular amount of money at time 1 in terms of time 0 money, how would you change this into a monetary value? In other words, how would you account for the growth of inflation on this value? Well, you'd say A0 times 99 over 97. And if it was here at time 2, you'd say A0 times 105 over 97, because this is still in terms of time 0 money and you want to change it to time 2 money. So that's how the inflation indexing work, how you account for growth using the indices. It turns out if you want to describe a monetary cash flow at a particular time, you just multiply it by the inflation index at that time over the inflation index at time 0, where Q is the index, QT is the index at time T, Q0 is the index at time 0. So to account for the inflation growth that happened from time 0 to time 2, you just multiply A0, which is the real value, time by the index at time 2 over the index at time 1. This should give you the growth over this period. And the same applies over this period. Okay. Now, Likewise, if you're given future cash flows, so if you're given A1, these are monetary now because these are future cash flows at specific times in terms of that time's purchasing power. For this example, if you're given these future cash flows to get the real values, so the real value of 1, for example, you just discount the growth in this period that was due to inflation. So you multiply A1 times 97 over 99. The real value for 2 is A2 times 97 over 99 over 105. So discounting the growth due to inflation due to this period, and in general, the real value at time t is equal to the monetary value at time t times the value of the index at time 0 over the value of the index at time t. So in other words, you just reverse this to get the real values. Okay, cool. I hope that makes sense so far. But because this is AXA and this is FinMath and life is never supposed to be easy for you, there will be a bit of complications along the way. And these complications will be, they'll tell you that the retail price index or CPI is lagged by 2 months. Or no, let me not say by 2 months. Let me say it's lagged by 1 period. In this case, a period will be a year. So it's lagged by 1 year. Okay. So what does it mean when I say it's lagged by 1 year? If it's lagged by 1 year, it means the value that is here, let's say the value of that is here is 97. It means this value came 1 year premature. It's 1 year premature. It does not represent the index at time 0. It represents the index at time 1. Likewise, the value that is here, let me just copy the ones that I had here, 99, 105, 108. Likewise, the value that is here does not represent the index at time 1. It represents the index at time 2. It's premature. The value that is here is not the index at time 2, it's the index at time 3. So to get the, I'm just going to copy down this timeline, yeah. So these would be the values of the retail price index with lag. And to remove the lag, the RPI without lag, you just move this value 1 period that side. So here would have nothing in this case. Usually they would give you another one. They would give you the value of the index at time -1 so that you can move it forward as well. But in this case, I have nothing there, so it's fine. Here it's blank. Here you'd have 97. Here you'd have 99. Here we'd have 105. Here you'd have 109. Here we'd have 108, 109. Okay, so these interesting complications are what makes FinMath fun, I would like to say. Well, because now there's a difference between there will be a difference between how we inflate and how we deflate values. Okay, so when wanting to get monetary cash flows, for monetary cash flows we'll call them CT. Né? The monetary cash flows will be equal to the nominal values. Remember, the nominal values still have to be transformed into monetary cash flows. That's why here we have the monetary cash flows as what we're changing into. We have the nominal cash flows, the nominal values is what we're changing into monetary values, because they're not monetary or real, so they're susceptible to be changed into monetary cash flows. So we take the monetary value, and to inflate it, we use the indices without lag. Okay, so would say Q. I forgot the notation that they use to this. They use for this, but would say T minus lag, I think, over Q0 minus lag. Yeah. So for example, if something was at time 1, The lag is 1 year. Okay, so we use the indices, the index to inflate it. We use the index at time 1 minus the lag period, which is 1 year. So we'd use the index at Q1 minus the lag period, which is 1 year. So we'd use the index at Q0 that we're given, which would be 97, which is the one we have after removing the lag here. So 97 over Q0 minus lag. For example's sake, I'll say this was 95. So we'll have 95 here. Over Q0 minus lag. Q0 minus lag, the lag is still 1 year, is equal to the value of the index at time -1, which is 95, which is precisely the value of the index that we have here after removing the lag. So to get the monetary cash flows, we multiply the nominal value by the inflation indices without lag. Okay, and then to get the real values at time t, you take the monetary cash flow at time t times Q0 over Q1 over QT. So here we don't mind the lag, we don't care about the lag. We deflate it using the ones that we're given. So if we're given a monetary cash flow here and want to get the real value of this cash flow, we just say 97 over 99. We don't worry about what's the lag here, what's not the lag here. The lag comes into play when calculating the monetary cash flow, where we use the inflation indices without lag. This will make it easier for you. Because T minus lag is just basically the inflation index that came before T. Yeah, the inflation index that came before T, if the gap between T and the period before is the lag, in which case it is the gap between successive times is the lag, which is 1 year. So the index without lag is just the index in the time before. The index at time 1 without lag is just the index in time 0. The index in time 2 without lag is just the index in time 1. Index at time 3 without lag is just index at time 3. Yeah, so to get the monetary cash flows, we use the indices without lag. And to get the real values, we use the indices with lag. This makes things a little bit interesting, right? Going back to our example of like the 0 coupon bond that is redeemable after 1 year at 105 nominal. So to get the real value of this, of 105 nominal, remember it's after 1 year, we first say 105 and we transform it into a monetary value by saying T minus lag, which is at time 1, which is 97, over 0 minus lag, which is 95 over 95. This will give you the monetary cash flow. And then to get the real value, we further multiply it by Q0, which is 97, over Q1, which is 99. And what we see is that these two factors, 97 over 95 and 97 over 99, they don't cancel out. It's not the case of 1 times f to the times 1 plus f to the minus 1, where it becomes 1. They don't cancel out because 1 is when you account for inflation, you take out the lag. When you adjust for inflation, you don't mind the lag. So this is where that comes in. So yeah, this is what we've done so far. I hope you understand so far. You can take a quick minute to pause and breathe and relax and rewind if you didn't understand. But we're just gonna do one beautiful example to tie it all together, just to make sure that you have this all in your head. Okay, so here's the example that we want to do. Just want to pick a nice color that pops out. So here's the example that we want to do. I'm going to take out a few things that you guys haven't done yet, but yeah, let's just read along the question. So I like to highlight important information so that I can be able to break it down for myself and to piece together the puzzle that I'm given from the problem. So firstly, we have the date of issue of an index-linked bond. So on 1 June 2007, it was issued. which were redeemed at 1 June 2009. So the term for this security is 2 years. Okay, that's worth noting. I don't know how, but somehow it's worth noting. And each bond was for a nominal capital amount of 100. So you see, we're given a nominal value. We're not given a monetary cash flow, a real cash flow. We're given a nominal value and a nominal coupon rate of 4% per annum, payable half yearly in arrears, and a nominal redemption price of 105. The actual coupon, and this is very important, I want you guys to note this, the actual coupon and redemption payments were indexed according to the increase in the retail price index in the period 6 months before the bond issue date and 6 months before the respective coupon or redemption payment dates. And the issue price was 93%. So when it says actual coupon redemption payments are indexed according to the increase in the retail price index, it means this nominal value, because this value, it does not give a sense of what it's actually worth today or tomorrow in any time in the future. We're just given a value. These are percentages of a face value. The face value is 100, and we have coupons of 4% of 100. We have a redemption of 105% of 100. So, but we don't know what it's actually worth. But the good news is we can use the RPI to inflate it to certain times, to inflate these amounts to certain times, using the indices to get the monetary cash flow. This is what I was talking about, that the nominal cash flow has no real value. It has no, like, we don't have a sense of what it's actually worth, but we can get what it's actually worth by first turning it into a monetary cash flow using the RPI and then changing it into a real cash flow. And then we're given the retail price index for different dates, whatever. Another thing I wanted us to note is that the retail price index is given in the period between 6 months before the bond issue date and 6 months before the respective coupon or redemption date. What does this tell you? That the indices are given 6 months prematurely. So what does this mean? There's a 6-month lag. The lag is equal to 6 months or 0.5 years. Okay, and you can see here the issue date is June 2007, but we're given the index for December 2006, which is 6 months before this. So it means this is Q 0 minus lag, and this is the end of term. An investor purchased 100 bonds at the issue date and held them until they were redeemed. So he or she held them for the full 2 years term, and the investor is subject. So we're going to cancel out the tax stuff because you guys didn't do that yet. But don't worry, I know you're excited to do tax in FinMath, so you'll get to do that later and enjoy all the complications that come with it. And here, calculate the real rate of return per annum and obtained by the investor. I just want to emphasize and note something, that we use the real rate for real values. So before we even think about solving for this, we have to somehow get real values. Okay? Cool. So now that we have outlined kind of the parameters of our problem and what it entails, we can now start to get to solving the actual problem. Okay, so like I said to you guys before, and I'll continue saying until the end of time, a timeline will save your life. Timelines save lives when it comes to FinMath. So the end of term is 2. I'll just do this minus 0.5 here. 0, 1, 0.5, 1.5. And the date here will be, we're given as December 2006. I'll take it as the 1st of December, because we go from the 1st of June. So I'll take it as 1/12/2006. This will be 1 June 2007, 1 December 2007, 1 June 2008, 1 December 2008, and 1 June 2009, which is the end of the term. Okay, and now we have just the normal indices that were given, which will be 105 at December 2006, so 105, and it'll be 107 here, 109, 110, 112, 116. Okay, now just to jump the gun and to, kill the mouse before it becomes a problem, I don't know, we're gonna do the RPI without lag. So the lag is lag is equal to 0.5 years. So QT minus lag is equal to the value of the index at t minus 0.5. Here, at t is equal to 0, the value of index without lag is equal to the value of the index at 0 minus 0.5, which is minus 0.5, which is 105. Like I said, you can just push it forward, because coincidentally the gap between our periods is the lag. So that's very good for us. We can just take the one that came before. Just take note that this is not always the case. We're just very lucky. Either that, or I just picked a very specific example that makes things easier for me. So here we'll have Q 0.5 minus 0.5, which is Q0, which is 107. You'll have Q1 minus 0.5, which is Q0.5, which is 109. And the same follows for the rest of these. Okay. Now remember, we use these ones without lag to inflate or get the monetary cash flows. And we use this one just bare as it is to deflate or get the real cash flows. Okay, cool. So now we actually need to get the nominal amounts that are at these times, because we need nominal amounts so that we can turn them into monetary amounts, so that we can turn them into real amounts. Okay, so the issue price, or the nominal amount at time 0, is 93% of 100. Each bond, let's see this is very subtle. Each bond is worth 100 rand, and this person bought 100 bonds. So how much does he have nominally in terms of bonds? How much are his bonds worth? I'm gonna say bonds worth is equal to, he has 100 bonds. Each of them are worth 100 rand. So 100 bonds times each of them is worth 100 rand. We'll have 100. Yeah. Take out a calculator here. 100 squared. You're gonna have 10,000 worth in bonds. Okay, and the price is equal to 93% times 10,000, which is 9,300 or 9,300, because they said the price of issue is 93%. So 93% times 100, and that goes for each bond that he bought. Okay, so here we have at time 0 we have 9,300. Now, because it's at time 0, it's automatically a real value, because it's an amount at the present time. Okay, so it's automatically a real value. But we'll see that later with the calculations. And the nominal coupons will be, here we're told that the nominal coupon rate, the nominal coupon rate is 4% per annum, payable half yearly in arrears. So it's per annum, payable half yearly in arrears. So it's payable half yearly. So we say to get the coupons, which are paid every half year, we say 4% divided by 2 times 10,000, which is equal to 2% times 10, 200. These are the nominal coupons. So the nominal values here, we have 200, 200, 200 as the nominal values. And the redemption, the nominal redemption, is equal to 105% times 10,000, which is equal to 10,500. So here we'll have the redemption 10,500 plus the last coupon 200 to get 10,700. Good people, these are nominal values. They are nominal values. All of these 9,300, 200, 200, 200, 10,700. So first we get the monetary cash flows. Monetary cash flows, okay? The first monetary cash flows, I'll call it C0, is 9,300. It's already at time 0. So the monetary cash flow will be the RPI without lag at time 0 over the RPI without lag at time 0. So it's times 105 over 105 to give us 9,300. This is why I said this is already a monetary and a real value, because it's already at time 0. Any value at time 0 at the present time is a nominal, monetary, and real value all at the same time. I don't know why it just works, so let's just use what works. And then at C1 we'll have 200 times, remember we inflate using these ones without lag, so times 105 over 107 over 105. So 203,8095238, which will store as A, and we will do the same for all of them. And so after doing the calculation for the rest of the cash flows at time 1 up until time 2, we get C1 is equal to this, and I'm storing these as these values on my calculator, and these are monetary cash flows at each time. And the next step, of course, because we want the real rate, we first have to get the real cash flows, which I'll call RT. And so the real cash flow, the first one is trivially 9,300, because to deflate it back, you'll say 9,300 times 107 over 107, which is just going to be 9,300. The second real cash flow will be A, which is the monetary cash flow at time 0.5 times, we use the ones with lag now, so we're going to say times 109 over 107, 109 over 107, to get 200,0699036, which I'll store as A prime. I've just put A prime here. I'll store it as A on my calculator, and we do this for each and every one of the real cash flows. Sorry, I just realized now this is supposed to be 107 over 109 because we're deflating here, and then this will be 107 over 110 to get 201,9567099 to store as B prime, and we do that for the rest of them. And so after calculating the real values, the corresponding real values for each of the monetary cash flows, we have A1, A prime, B prime, C prime, and D prime. And now because we have the real values, we can form our equation of value using the real values. So we'll have 9,300 is equal to A prime, and it's at time 0,5, so V 0,5, and this is at the real rate R because we have real values now. B prime VR1 plus C prime VR 1.5 plus D prime VR squared. Okay, now a useful trick when using this, because you're obviously going to use your financial calculator to solve this, is that since it puts the cash flows at discrete natural times, i.e. 0, 1, 2, 3, and not the decimal times, the ones in between, or rational times 0, 0,5, whatever. You can say 9,300 is equal to A prime V1, but this will be the semi-annual interest rate. So this is the semi-annual real rate, and this will be after the first half year plus B prime VR squared. This is R2 over 2 plus C prime VR3. This is R2 over 2 plus D prime VR4. This is R2 over 2. And when you solve this using your financial calculator, the answer that you get, it's very important that you realize it's R2 over 2. So it's the semi-annual effective real rate, which is 4,73098,3591%. And so to get R, you just say 1,04730983591 to the power of 2 minus 1, which is 9,69%. And that is your real rate. But the answer is, I don't think, as important as how you got there. So firstly, you get your nominal cash flows, you inflate them to get your monetary cash flows, which you deflate to get your real values, which you then form an equation of value using your real values and your real rate. You cannot find the real rate unless you have real values. That's the point that I was trying to hammer across. And of course, because this FinMath would like to make your life more difficult, you can't just give your R and say from the financial calculator, because in most cases they'll ask you to do this via linear interpolation. So what you do is that you cheat and you solve it using your financial calculator, and you act like you hide this step, by the way. So you'll hide this step, this whole shenanigans, you hide it. You act like you went from here to saying, oh, let me guess. The formula for linear interpolation is that R minus R1, R2 minus R1 is equal to PV minus PV1 over PV2 minus PV1. These are the interest rates. These are the corresponding present values at those interest rates. You cheat. You know the answer is 9,69%. So you guess, let's say R1 is like 9. You say to the second decimal place, you go 1% lower. So 9,68%. You act like you're guessing, and then you calculate the corresponding PV1 here. And then you say, let me say, okay, that one looks a bit too low or high. Let me change the interest rate and go 1% higher. So you then have 9,7%. Then you have your corresponding PV2. And then you just plug these in to approximate R by saying PV minus PV1. Because this one you have anyway, it's 9,300. You'll always have, it'll always be on the left-hand side of your equation of value, or right-hand side, depending on how you want them to be. R2 minus R1 plus R1. So this is how you're supposed to do it. You must hide this step and you'll get an extra few marks for this. But you should ultimately arrive at 9,69%. Okay, cool. I hope you guys understood that. I know that was quite a mouthful at times, and it sounds like I was saying a lot of things at the same time, and I tend to be quite fast. So if you have any questions, you can leave them in the comments, or just ask me on our group chat, or if you see me in person, or you can ask me in person as well. I'm very approachable. Or in the TUT, you can ask me in the TUT. But yeah, that's basically inflation, money, and real rates. Okay, see you guys next time.